being a professor kind of guy, I'm going to do a short lesson on forces, and then I'm going to show you a bunch of videos about what you get from that when you build a robot with it. I've got some other stuff. Don't let me forget to show this to you before we finish.
Magic trick.
Soon. So I'm really into force control because I like robots that physically interact with the world. Position control is good if you don't mind, kind of scratching things. If you need to be precise, like your routing or your milling. Force control, though, is interesting because if you need to wash a window, you don't want to punch through it. You want to conform to the constraint and exert a certain amount of force. If you're putting things together, position control won't do it. Those threads will jam. So there are lots of good reasons to be able to control forces. It's not trivial. You can't just go buy a servo, buy a big one, and put it together. But what you get for it is some interesting things. So first, I want to make clear we know what a force is. Some of this is like old hat to some of you, and for some of you this is not. So a force is something that acts in a certain direction. It's something that can do work. And it has a direction, it has a magnitude, and the more subtle thing is that it has a line of action. So if I'm pushing here, it has a very much different effect. Same direction, same magnitude, but it has a different effect. So where that force vector is coming from is important. And force is different from pressure. Some people call force pressure. Pressure is force per unit area, not just force. So I'm going to talk about two different control methods. Sorry, forgive my sketchy drawings here. On the top we have position control, and what it is for me is a very highly geared connection between the motor on the left and point here, yeah, and the link that we're driving on the right. So the advantage is you can have small motors with big gear reduction, so you can fly the motors out here, and it's not too much of a burden. The downside is it's not back drivable. If I push on it, it doesn't go back. That's bad news if I bump into it or if it hits me. The other extreme would be a cable drive, as shown on the bottom. And there I've got actually a fairly big motor driving through a belt, or actually cables. There are reasons you want cables. And the nice thing about that is that it's back drivable. If I push on that link, the motor spins and gets out of the way. And in fact, the motor can serve as an actuator as well as a sensor. Because if you tell it to hold a position and then you push it, the current has to go up to hold that position. So the current going into the motor lets you know how much force is being exerted on the outside. In the middle, we have series elastic actuation, which has a motor in size, could be as small as a position-controlled robot, or probably midway between the two. So it has springs in the two cables, or the actuation, so that you can have a small motor, and the way you get to control the force is making small motions of that motor in order to vary the amount of stretch in the springs. And you can measure the stretch in the springs, so therefore you can sense the force or you can control the force. Now you're going to see why people call me crazy. This is ways to use cables. And N is the number of motors that are required to do this. And on the top, I've got one motor pulling on a cable, and then there's a spring pulling it back the other way. I don't necessarily like to do it this way, but it's pretty simple. If you want to do a force controllable arm, this is conceivably a good way to do it. This second one down is what I typically use, and you'll see some arms that use that. This next one, a little different. It's more like you have a muscle on one side and one on the other side. And so you activate them differentially and you go up and down. If you co-activate them, nothing happens. For those who do math, the co-activating is the homogeneous solution, or the null space. So you actually can do something with that. You can tighten up both of those motors, and it'll increase more friction, so it effectively can break the arm. Or you can loosen. There's a whole lot. I could go on at length about that. So the bottom one, where I get really crazy. Well, sorry.
Can I interrupt for just a second?
Yes.
You can still use your hands if you can clip this on you. Would that be
sure.
We'll try that. Yeah. Just try and get it close to your mouth as you can.
Testing. Okay.
Much better.
There. Okay. Thank you. So there's something I thought I invented, which I call N+1. And it's hard to explain. But instead of having to have two N motors, a pair of motors for each joint, or just one motor for each joint and two cables, there's a way you can route the cables so that if you have, let's say, two joints, you can have three motors to control that, and just three cables going out there. So two joints, only three cables instead of four cables. It gets much better if you have six joints. You only need 7 cables. Again, I thought I invented that, but it turns out elephants do that, and somebody else noticed that. So I'm going to show you some videos that make use of the principles I just gave you for doing lots of interesting things. Tony, did you, wherever you are, did you talk about the PR2? No? Yeah?
Yeah.
You did? Okay, because I'm going to show just a vignette out of that, but yeah, I'm not going to do the whole thing. So first, PR2 was the second generation. The first one we built in my lab out of using a laser cutter, built out of wood, about 18 months top to bottom, 23 degrees of freedom. And it was, well, I'm not going to tell you how it's controlled, but we got it to clean up a room. And it was kind of slow, and it was learning, I'm kidding, but it can go a lot faster. And when it goes fast, it's like, to me, it's really cool. The point of doing this, we wanted to prove to potential investors or whatever that it has the physical capability to do a tremendous amount of stuff. This is 8 times normal speed. So,
What year was this, Ken?
I don't know, about, 6 years ago,
Wow.
maybe a little more. Yeah, I mean, this is so much. Well, part of one of my dreams was to have a robot that was on wheels. And could go get me coffee, and thanks to Tony, it did go get me coffee. And I don't care that it was cold. So you can see some evidence of force control. The reason it didn't break the table is because it could hit it and move along. It didn't have to be precise. Force control let you be exactly precise. I touch the surface and I stop going. I don't have to measure it. I don't have to scan it. So the same thing happens here with unloading the dishwasher. If it bumps into something, it's fairly gentle. And to grip it, it doesn't break the plate because it's off center. You'll see another example of how compliant the arm really is. Your control system's got to be a little more sophisticated. Instead of just being dead on positioning, you have to allow for it to be somewhat compliant, which is a good feature. If you're picking up heavy things, you have to be careful. And this one I love. He's going to smile. I don't know why he smiles so much at this thing, but. So what's going on here? It's a backdrivable arm. You notice he could push on it. He doesn't have to fight it or get away from it. It's a fairly simple way to get a force controllable arm and make it backdrivable. There's a much more difficult and less physically robust way, which is you have a position control arm, but then you put a force sensor out here so you can detect when it's being pushed on and have the motors getting out of the way. But your bandwidth is going to be less. You've got the fragility of this. There are some commercial robots now that have torque sensors in each joint and use harmonic drives, but that's too complicated. I don't have patience for too much complexity. Okay. So you're going to see here in a minute a picture of me before I started dyeing my hair gray and blue. And you'll see what that means in a minute. So this is my thesis project. This is high-strength aircraft aluminum. I wanted a hand that you could drive over with a truck and it wouldn't break, because I got tired of fixing things in the lab. I wanted to use them. So it's been programmed just to do some simple exercises. You'll see it manipulating things. There's an interesting thing going on with the trajectory here. Typically, if you time versus theta, if you want to make an arm move, the easy thing to do is have it change its angle over time, then change the angle over time, going up and down. But those square corners are discontinuities in acceleration, where it's jerk. And so you want a jerk-free trajectory. And that's what we have. We can't instantaneously change are actuation forces. And so when you make this a jerk-free trajectory, it looks, it's smoother, we can relate to it a little more, it's not like this stereotypic robot motion.
Much bigger than our own hands. Manipulate the cam. It moves to close around the cam and then adds a bias force to retain the graphs. And then we follow the nominal trajectory. Although our description of the motion was not precise, it's able to retain the graphs throughout the motion because of the forgiving properties of the stiffness control. Next, we give it a different size object, which has a slightly different stiffness specification. You can see that the hand is also capable of executing motions that are very small and precise. This type of motion is appropriate for assembling objects in tightly constrained situations. As you can see, to quite a large degree, we have achieved the goals of increasing the dexterity of a robot hand. Here we've commanded the hand to grasp the string from the inside. It exerts an outward directed bias force to retain the grasp on this object. You can see the fingers move together. For motion in all other directions, it's relatively stiff. So that if the hand is holding an object, that object.
Yeah, towards where it does there. Come back to this in a minute. So yeah, that was an incredibly fun project, and you know, somewhere I have to draw the drawings that are drawn with a pencil, and they're gorgeous. The arrows are kind of cute. And anyway, it had the ability to control forces. That's why it could grasp something of an uncertain size, because it would conform to it. I talked about stiffness control in there, and that means that I can make it compliant in one direction, but stiff in another direction. So for example, if I'm putting a peg in a hole, I've got a hole here and I want to put my peg in. So I want to control the position in this direction. Sorry, I want to let it be compliant in this direction. So I can push up against the constraint surface and slide around on it, and I won't gouge or hurt anything. But I want to make it, forgive me, stiff in this direction, so it goes where I want it to do, but compliant in this direction plus a force. So I'll move around and then it'll slide into the hole. There's a lot more behind that, somewhat inspired by industrial concerns of putting pegs in holes very fast, and this is echoing a way to do that that's programmable. So one of the things that Tony did that particularly warmed my heart was he used sensors that involve contact to perceive the world to help guide what the robot is doing. So instead of taking a picture or using the Kinects, which didn't work in this case because it was up against a glass wall.
And it was outside.
Okay, yep. We had to choose whether it would bend at the waist or telescope, and I think in the end telescoping was good. Okay, so it's trying to figure out, and Tony, correct me on any of this, but it's trying to figure out where the window is to get the distance right. And it's also intentionally positioning itself to the right of the handle that it's got to grab. Now it's felt where that is too. So it has the forward and back and the left and the right information that now it knows index over, close, and I got the door. And this also validates something else we put into the robot, which is we wanted it to be able to spin around its own axis. So it's kind of pure. It's not just because it's elegant dancing for dancing with, but it's highly functional. And So this is not quite as old as the video of my hand. So we built an arm called the WAM, whole arm manipulator. It's been commercialized. It's sometimes called the world's most dexterous arm, whatever dexterous means. It uses cable drives. It's very good at force control. In fact, we worked very hard to make it have high bandwidth and force control. Turned out having that kind of bandwidth also makes it very fast moving around at high accelerations. For those who know about impedance matching, there's a mechanical version of that, so you deliver maximum power to it and therefore get maximum acceleration for a given motor. This is really cool too. So first, the setup. We've got the blue arm here in the center. Cable drives down here, cable drives going out here. Another advantage of using cable drives is you can locate all the motors down at the base, so you're not carrying around a lot of mass. And it can be very long and slender, which is what we're going to get to here in a minute. There are cameras mounted up on the ceiling, so they're stationary, looking over the scene. They're color keyed, so all they can tell is white versus black. You'll see what the eyes see here in a moment. And the way it finds the ball, one camera scans until it sees it, centers the blob on it. The cameras are steerable. Then the other camera's smart. It just follows that line down until it intersects with the ball. It does this at about 30 hertz. So you only get a couple frames before you got to catch the ball.
Whoa.
Watch the eyeballs.
Wow, okay.
It's like a little dog. If you move the ball around, the eyeballs are kind of tracking it. It's really cool. One of the hardest parts was getting the hand to be fast enough to close on time.
Yeah.
You notice how it's following it. I mean, the eyes are following it, and the robot's being guided. Because it knows how to catch it, it also knows where it came from. So it goes right back. We should have gone to the baseball commission for funding. It would have been better than the other guys. About 80% of the time when it's tuned up. Okay, if you'll indulge me for another 2 minutes, I'm going to show you some newer stuff.
So that kind of built off your original hand, right?
Inspired. Each one kind of piggybacks on the other, so it's a learning experience. So two things here. So the fingers on my hand, and most stop that, are fat, and I want them to be long and slender. And the reason is you can gain access to much more of your environment if you're long and slender. But that's kind of weak and maybe not so good with today's materials, but I'm not so concerned about that. That will be done. That will happen. What I'm concerned about is active perception. So we do this all the time. We're not just manipulating, we're also perceiving while we're manipulating, or sometimes it's perception dominant, and we're actually trying to feel around. So imagine a finger that's trying to find, well, what's the stiffness of the table? You can tap it. You can do system identification on it. Look at the signal from your accelerometers. Is it plastic or metal? Well, I could use an electromagnetic sensor to figure out the electrical impedance of it. I could put thermal sensors on here. So we've got a data bus in here, so you can throw whatever sensors you want in here, and you can probe things and learn more about them than what we learn about them. If you could do bioproperties, chemical properties, from there. So this is intended to be a platform. I don't have funding for it in case there are volunteers. And so again, I'm focusing on low forces but high active perception. Forces will come with better actuators, better materials, and so I'd like to get ahead of the game doing active perception. Kind of related, you know how you're at a party and you got a glass of wine or something and you want to talk with both hands and stuff?
Yeah.
We got a solution for that. Okay, this is my third arm. And it's not powered, doesn't have brakes yet, but brakes are the next step. Brakes with sensors, so you can tell it to stop at a certain place, click them back on at the same place, or maybe have multiple points. Then put motors on it. What do you do with this thing besides holding cocktails? Well, could hold my flashlight, could hold a little workplace, could steady me if I'm climbing on a ladder or if I'm physically unsteady. There's other stuff. You all know this is what you want. $200, as durable as a vacuum cleaner. Those are the goals. And in VR, people want haptic interfaces so you can pick up that basketball and throw it. This is that too. If I hold on to this thing and I've got my goggles on and I want to pick up something, I will feel the weight. There's some psychophysical issues around what will I feel like if I'm pushing on a wall. It'll push back, but if there's a reaction force on my back or whatever my harness is going to be. So if that might feel strange, it might not feel strange. Typical haptic interfaces are grounded on the table. So when you have a virtual wall, it stops it and it won't go through. So body mounted is kind of a science experiment still, but it'll work. Got a proposal in for funding this thing. If we get that funding, it's going to be a seriously good project. And a small anecdote, and then we'll go. I could only find 3 references for third arms. 2 of them were by an artist whose name is Stellark, and he puts an extra arm on his forearm, actually, and he has a pen at each one, and he kind of does this interesting performance art piece. And then there's a VR guy at Stanford who has a third arm. He's looking more at a sort of personal sense of space and extension of oneself, which is a really interesting kind of problem as well. I cited Stellark. 2 days later, he showed up in town. I'd never met the guy. He's from Australia. I'm like, what are you doing here? He said, well, I wanted to ask you about arms. It's like, oh my gosh. And anyway, very creative, very clever guy. He's next in line to get one of these things because he'll do interesting art with it. So that's it. I'm hanging out so we can talk about stuff. But thank you.
Questions?
Sure. Sir.
So does the third arm use the cable actuation, like you said?
I'm open to suggestions. Yeah, probably it will, because I do want it to be very light. And I'm thinking sort of like a fanny pack, so we've got a cluster of motors and batteries back here, and feed the cables through the joints. And the aspect ratio of this is a little unrealistic. It's going to get a little wider. It's going to taper down. So that's part of the research. And again, I'm not as much concerned about high forces as I am concerned about human-machine interaction. How do I tell it what to do? Do I talk to it? Do I touch something? Again, Tony, I have a laser pointer on my head and say, I want that, and go and get it. Can it anticipate what I need? Or if I'm starting to fall over because I'm weak, can I push on the world more and more and more? We can talk about this ad infinitum. Yes, Berkeley is going to have to be different. For the brake version, they got to be small enough and real torquey. For the motor version, same problem. Mounting the motors and brakes and everything else on the body rather than flying them on the arm will make a difference. Other questions? Okay, good. Thank you again.